Okay, today we're going to derive the kinematic equations. For constant velocity, the average velocity equals the slope of a position versus time graph when the object travels at constant velocity. As you can see in the picture, the slide, average velocity is v bar equals, and we have this delta x, change of position or displacement, which is the rise, over the time interval delta t, which is the run. So it's the slope of the graph, rise over run, rise being displacement, run being the time interval. If you need to find displacement when an object moves with constant velocity, a graphical approach is a nice thing to do, but it also involves the equation on the previous slide. The displacement will simply be the area under a velocity versus time graph. You can see this shaded area in here. That is the displacement. Now how do we figure that out? Well, we just find the area of this rectangle. It would be the height, this side right here, which would actually be up here at this top. We would know the average velocity, this y-intercept, times the base, which would be right here, which is the delta t, the time interval. So using that equation, it would be displacement equals height times base, or as you can see further above in the top line, displacement equals average velocity times time. If we're dealing with uniform acceleration instead, we would want to take a look at, sorry about that, the velocity versus time graph of something that is undergoing what's called uniform acceleration. And as you know from the lab, on a velocity graph, if the graph is a line, is linear, the acceleration is constant or uniform. The equation for this is simply the final velocity equals the acceleration times the time plus the initial velocity. This is a form of y equals mx plus b. Y is your final velocity. A is the slope of the line, acceleration, that's m. X would be t, your time interval. And v sub o is the y-intercept, which is your initial velocity right here. As you can see on the graph, it shows you the slope being rise over run, delta v over delta t, which would be a, the slope of the line. If instead we're interested in finding the displacement, it's still the area under a velocity versus time graph. However, this time, since the velocity is changing, it's not going to be a rectangle. It'll be, in this case, a triangle. Now, if you think about it, the area of a triangle is 1/2, as you know from geometry, base times height. Well, you can also write that as 1/2 height times base. In this case, the height, which we'll show you in the next slide, the height is delta v, which is over here. The base is delta t. So 1/2 the height, delta v, times the base, delta t, will get you the change of position, delta x, which is the displacement. Now, there are different equations that we can derive from this. We can take the slope of a velocity versus time graph, which is average acceleration, rise is delta v, run is delta t, rise over run is delta v over delta t. We can rearrange that to get that the change in velocity, delta v, equals the average acceleration a times the time interval, delta t. Now, if you come down to this equation from the previous slide, and we take delta v here and substitute for it a times delta t, we get the final line that you see at the bottom of the slide. Moving to the next slide, we can take the delta t's and square them. We end up with basically displacement delta x equals 1/2 the acceleration a times delta t squared. Now, assuming uniform acceleration and a starting time equal to 0, the equation can simply be written as delta x equals 1/2 at squared, which is displacement equals 1/2 times acceleration times the time squared. In the next slide, we can also find the displacement of an object that accelerates with a non-zero initial velocity. And we break up the area into two parts. This bottom area is a rectangle, and again, that would be the height times the base. Basically, that's the height, which is your initial velocity, VO, this part right here, times the base, which is delta t, this part of the graph as well. The product of those two, height times base, gets you the rectangle, which is part of the displacement. Triangle at the top is also part of the displacement because you're speeding up. So the second part is there's a triangle that represents the displacement due to the acceleration. And again, we've derived this from before. This displacement, the area of the triangle, is 1/2 a times delta t squared. Summing those two areas, we get this final equation. This is the rectangle part, v sub o times delta t, plus the triangle part, 1/2 a times the time squared, delta t squared. If the starting time equals 0, the equation can be written as displacement equals initial velocity times time plus 1/2 times the acceleration times the time squared. The big change is that we just basically drop the deltas in front of the t's. We can also find what's called a time-independent relationship between displacement, velocity, and acceleration. And sometimes it's useful to have an equation where if we don't know the time involved, we have ways to figure it out, figure out the other quantities. We can start with definition of average velocity, which is displacement over time. And we have another way to express that, which would be the final velocity minus initial velocity, the sum of those two, divided by time. That's the simple average of two numbers. And Galileo figured out this relationship, and he realized that when you accelerate uniformly, the average speed is what he called the middle speed. And another way to say what that is the final velocity plus the initial velocity. The sum of those divided by 2 equals the average speed. Now what we're going to do is we're going to take the acceleration equation, definition of acceleration, change in velocity over change in time, switch the a and the delta t algebraically, which is legal, so the delta t equals the change in velocity over the average acceleration, but change in velocity equals the final velocity divided by the initial velocity. So we have delta t equals final velocity minus initial velocity, that difference divided by the acceleration. In the next slide, we take the equation for displacement, delta x equals v bar, average velocity times t, and we make substitutions. And the substitutions go like this. The average velocity is this new equation we just developed 2 slides ago. Delta t, we derived this 3 slides ago, and we basically put them together in the next slide. So the displacement equals the average velocity, which is this expression right here, times delta t, which is this expression right here. And then we're going to basically multiply a fraction, 2 fractions. Multiply the top, the 2 numerators, and we multiply the denominator in the next slide. And we can see that the denominators multiplied give us twice the acceleration, 2a bar. Vf plus Vo times Vf minus Vo is the difference of squares. When we do it, we get final velocity squared minus initial velocity squared. In the final slide, or near the final slide as far as the derivation goes, is we rearrange things so that we multiply both sides by the denominator. We get 2a times delta x equals final velocity squared minus initial velocities. Now in the next slide, we're going to solve it finally for final velocity squared. We're going to add the initial velocity squared to both sides. We're going to end up with the final velocity squared equals the initial velocity squared plus 2 times acceleration times the displacement. Now, which equation do I use and when do I use it? That's the next issue. If you can keep this straight, this is not hard stuff. Basically, you want to find out, in a given problem situation, which model is appropriate. Is the object moving with constant velocity, in other words, the constant velocity model, or do we have a situation where the object is accelerating uniformly, which is the uniform acceleration model? Now, once we make that decision or determination, then we can basically decide whether to use an algebraic approach or a graphical representation to figure out the unknowns. Constant velocity. We can use the algebraic approach for average velocity, which is displacement over time, or we can find the slope of the position time graph, which is actually using this equation, which shows you rise over run. If we have displacement for constant velocity, we solve the previous equation for displacement. It equals the average velocity times the time. But this equation, if you think about it a little bit, this is the same equation that would figure out the area of this rectangle. So if we take the height times the base, this equation can be applied to a graph of velocity versus time. For uniform acceleration, we have the algebraic form of the final velocity equals acceleration times the time plus the initial velocity. We can rearrange this equation to solve for acceleration. If we solve this equation for A, we get that the acceleration equals the final velocity minus initial velocity over the time interval But that also equals what's in the middle here, which is the slope of a velocity time graph, rise over run. Also, we can find the displacement. Algebraically, we can use this equation. Displacement equals the initial velocity times the time plus 1/2 times the acceleration times the time squared. Now you can eliminate this term right here. This term right here could equal 0 if the initial velocity equals 0. Then you're left with displacement equals 1/2 the acceleration times the time squared. The other thing you can do is draw a graph and figure out the sum of these areas, the rectangle plus the triangle. If you don't know the time, you can go to this time-independent equation. The final velocity squared equals the initial velocity squared plus 2 times the acceleration times the displacement. And this can be rearranged algebraically to suit your needs to solve for any unknown of these 4. If you know 3 of the 4, you can solve for the missing 4th one. And that's basically it. To sum up, we have all the equations in one place. We have the constant velocity equation, solve for average velocity and for displacement, and we have several uniform acceleration equations. This is basically solving for acceleration. This is the same equation solved for final velocity. This is the equation for displacement, and this is finally the time-independent equation. So there you have it.